All right, so today a quick lecture on the product and quotient rule. Now, these are rules that help us differentiate functions that are products or quotients. So h is f over g, or h of x is some f of x over g of x. I alluded to 2 lectures ago why we can't just make it be f prime times g prime. Wouldn't life be so much simpler if we could? But we can't. So it just doesn't work out based on how we've set up our definitions. So we got to figure out what's going on. There is a way to get through this using the limit definition of the derivative, and it's been beat to heck. It's a nice simple proof, and I'm just going to link a video of somebody who's done it before, because I'm not going to add anything to that. But what I can add to is a visual and intuitive explanation of why this is the case. All right, so I'm going to do that and then link the proof, which I'll expect you to be fluent in, not necessarily recreate, but again, it's been done since Calculus 1 started, so I don't need to do that. What I do want to give you is the reason why. And so I love this visual. This is from Better Explained, which is a great website. And so this explains the logic behind the product rule with a graphic using area, right? So if you denote the product of f and g as like a length times width of a rectangle, then what we can think about is that when we nudge x by dx, right, we wiggle this little input, which is really what dx is, right? We kind of shift it a little bit like a dial, I like to think of it. So when you wiggle that dial for x, what happens? Well, f, since it's taking x as its input and it has its own output, and same with g, these things both wiggle as well, right? It's like the reverb and echo on an electric guitar. Both of these things, when you turn that dial, change by a certain amount. That amount is changed right here. So right here and right here, those are kind of like the response to the input wiggling. Whereas this in here is the total amount, this is the total output of h, which is f times g. So again, you can think reverb times echo, or temperature times altitude, whatever your product of functions might be. This is your main output, and then this is the change when you mess with the input. So when we do that, what we get is this box, the net change here and the net change here, are given by these expressions. The wiggle of f times g, right, because g is really this length here. I know I'm cluttering up this picture a little bit, but g is this length right here. F is this length right here. And so the area of these two boxes is given by these two. So this is df times g, this wiggle, df times the length g, and this guy, dg, which is right here, dg, times this length f. Okay, so what does that tell us? The nudge of f times g, the nudge of g times f, these are both a part of the net change when we wiggle the input. That's how this whole rectangle changes. And what is the rectangle? The rectangle is h. The rectangle is the output. So when we change x, the dimensions change in such a way. Now you might be asking, hey, Mally, what about this little guy up here, this corner? This isn't a part of the rectangle, but it seems to have some area or something to do with this. Well, df times dg, what we say is that it vanishes. And the reason for that is, if you think about how small df really is, let's say it's 0.001, and dg is something similar, maybe 0.002. If we multiply those things together, that becomes so incredibly small, it's not adding anything to the area. Okay, so it's vanishing much faster than anything else. So we can assume that this actually goes to 0. These are both infinitely small quantities, the df and the dg. All right, so this is an explanation for the rule that I'm about to give to you, which is, all right, how does f change, or how does h change? Well, let's write this up here first. Then the derivative of h of x, which is the derivative of f of x times g of x, that's going to be the change in f times g plus the change in g times f. So another way you can think about it would be using Leibniz notation as well. So you could say, instead of f prime, we could call it df dx, that wiggle, gx, plus dg dx, the wiggle in g, times f of x. And that's how much the area is changing. And so again, pointing back to this diagram, and I'll clear out this stuff here, now that you kind of know what's going on. If we're asking, how does this rectangle change? Well, this is how it changes, here and here. So the sum of those two things is going to be the net change. Okay, so just to explain with an example how this works, remember, if I've got my function, which is f times g, and then here's my df times g, and my dg times f. So here's my h. Then, if x squared is f and sine x is g, then this is what we're talking about. The wiggle of f times g, that's this guy up here, plus, right, the other part of the change, plus the wiggle of g times f. So that's why you need both of these things, and that's why it's not as simple as just f prime times g prime. We have to have it written like this. So it's the sum of these two different products of how both dimensions are kind of shifting, okay? So when you see a product of two functions, your brain tends to want this to be simpler than it is, because calculus can be complicated. But please note that when you have a product, you got to use the product rule. Now, this doesn't count for when one of them is a scalar. It will still work, because if one of them was a scalar, maybe I'll just highlight that real quick. If this were like a scalar 5 sine x, and I go to differentiate this, I would prefer that you use the rule for scalar differentiation, which is this is just 5 times cos x, right? But maybe you should verify that this will work using the product rule, even if you maybe don't recognize that. Well, you see, if this is f and this is g, well, the derivative of f prime is actually going to be 0 times g of x, which is sine x, plus 5 times g prime, which we know is cos x. And so that will work out. But man, is that a lot more work when it doesn't need to be, right? So if you have a scalar, if there is a scalar product, please just use that rule that we already know about differentiation. All right, and lastly, in a much less exciting way, is the quotient rule. I feel like the product rule is very intuitive once we break it down like that. The quotient rule, we can say it's similar, it's just a little funky, right? Division's always a little funky, and we kind of have to have it. But what I'll just do is give you the rule for that. So if you have a quotient of two functions, so let's say, maybe we'll give ourselves an example to work through as well. Let's say it's x squared over sine x, okay? H prime is still going to involve that wiggle of both functions, but it's going to be slightly different. So it's going to be f prime of x, g of x, minus f of x, g prime of x, all over g of x squared. All right. The fact that there's a difference here, there's that little corner is being subtracted off. It makes it a little bit wackier, but this is the statement of the quotient rule. So I'll show you just quickly how to apply it before you are set loose on some practice. And so if f is x squared and g is sine x, we know that f prime must be 2x. We know that g prime must be cos x. And so their derivatives are related in this way when we differentiate the whole quotient. Let me just write it out so you have a full thing here. So if this is x squared over sine x, then h prime is going to be, well, we've got 2x for f prime times g, which we said was sine, minus f, which is x squared times cos x, is derivative of sine, all over g of x squared, which is sine of x squared or sine squared x. And we can just leave it like this. We don't need to simplify it any further. And so this is just a quick example to show you how that works, and to note that the order really matters here. Since the order matters in division, the order is going to matter in the quotient rule. F needs to be F and G needs to be G, so F prime and G prime are set, and since there's a difference here, that's going to matter. Whereas with the product rule, you could kind of get away with, well, x squared times sine x is the same as sine x times x squared, so the commutative property works, and this order could be flipped, and that's fine. That is not the case here. Okay, so to just note that the order matters, maybe we'll put a little note here since I've said it twice. All right, so I'll let you guys get some practice on the derivative rules we've had so far. And I hope this helps, and we'll see you in the next one.